Hello, I'm Najmul Hassan and I'll be presenting the work done by my research scholar Nagamani and my colleague Dr. Priya Shah. Morphology of Galaxies in the core of Coma Cluster. Clusters of galaxies consist of hundreds to thousands of galaxies that are bound together by gravity. There are three groups of galaxy clusters: CD clusters, spiral rich clusters, spiral poor clusters. CD galaxy clusters are rich in ellipticals. Spiral rich clusters have composition similar to that of field, and spiral poor clusters are dominated by lenticular galaxies. The Coma cluster is a very rich and dense cluster at a redshift of 0.023, which corresponds to an approximate distance of 100 megaparsecs. This is one of the best clusters to study luminosity, environment, and morphological classification of galaxies. Extensive work has been done on morphological studies of galaxies in Coma cluster. Andrion, Gerbal, Kashikawa works of these are a few of those I'd like to mention. Coma is a CD cluster whose ellipticals, lenticulars to spiral ratio is 3:4:2. We have used publicly available data from HST ACS Coma cluster. It covers the core of the Coma cluster. 25 regions were observed by the wide field camera. Exposure time of 1400 seconds in the filter F814W were taken. We worked on 25 science images and catalogs from the archive STSI IDEO. We used the source extractor catalog and identified 77,787 objects. 594 galaxies were found brighter than 19.5 magnitude in F814W filter. We separate the extended galaxy, point sources, cosmic rays, and artifacts from the source extractor catalog. We tabulate and give values for flag objects of values 0, 1, 2, and 3 respectively. We found 219 objects whose celerity index was 0. This is the region of the Coma cluster, the stamp of the footprint of the observations, the 25 tiles which was observed. Yeah. We have used published spectroscopic and photometric data to determine membership of galaxies in our sample. Spectroscopic members were selected with a redshift range of 0.023 plus or minus 0.009. And the figure shows the F814W magnitude distribution of available spectroscopic data. Here the gray steps represent the HST ACS Coma cluster source extractor data. Pink represents the data points, and blue represents the data points, and the green represents the data points. Galfit was used for profile decomposition. Galfit is a luminosity profile decomposition software that fits 2D analytic functions to the luminosity profiles of galaxies and point sources directly to digital images. The functions we can fit are exponential, Cerseic, devacular, and Gaussian, and many others. It allows for simultaneous fitting of arbitrary number of components and combination of the above function forms. More functions can be added as per the requirement of the user. Single Cerseic fits were done initially, and then bulge disk fits were done using two components with Cerseic indices n and 1. The Cerseic profile is one of the most frequently used functional form and is given by this expression. where IR is a specific intensity at a distance r from the center. IE denotes the surface brightness at the effective radius RE, and RE, the effective radius, is the radius that half of the total flux lies, intensity lies. N denotes the Cerseic index. Exponential and Gaussian functions are special cases for the Cerseic function when n equal to 1 and n equal to 0.5 respectively. The fitting has been done iteratively with the optimal choice of initial parameters. We use the parameters obtained from the source extractor catalog for each galaxy. Here's a sample output. On the left, we see the science images. The center ones are the models which GalFit fits, and on the right we have the residuals. So if you subtract the model from the science image, you get the models. And what we notice here is if the residue is almost there's nothing in it, it indicates that the model is a good model we have fit. But very often, what meets the eye from science image and what is the actual morphology after this decomposition and subtraction of the model gives you the finer features. For example, the one in the center, the one on the left is the science image, and it appears like a elliptical galaxy. But when you subtract the model from this, you get spiral arms. And in the lower row, you see it looks like a spiral galaxy. And from the residue, you see that it has a bar feature as well. So these are some of the examples of these. Using spectroscopic redshifts, we segregate the galaxies in a sample into cluster members, non-members, unknown redshifts. We further separate them into dwarfs and non-dwarfs. For members and non-members of the cluster based on the absolute magnitude of the galaxies, for MF814W less than minus 8.5, this is the criteria given by Marinova. We have used the same criteria. And to calculate the absolute magnitude, for members we have taken the distance of 100 megaparsecs, which corresponds to the distance modulus of 35. For non-members, we have taken the individual redshifts values to calculate the absolute magnitude with Hubble constant 69.8 plus or minus 0.8 kilometers per second per megaparsec. We found that 132 members, 51 are non-dwarfs, 81 are dwarfs. Among the 32 non-members, 4 are dwarfs and 28 are non-dwarfs. For the remaining 55 galaxies, we don't have redshift information, and hence we are unable to identify the dwarfs. This table shows the morphological classification in terms of percentages. So we have the morphological types: ellipticals, lenticulars, CDs, ellipticals, barred lenticulars, and so on. And in the second column, we have the percentages. 18% are ellipticals or lenticulars. CD, they are just 2%. And we have a lot of lenticulars, 29%, and lenticulars with bars, 22%. For non-members, these are the figures. And for unknown redshift galaxies, these are the values: 13% for ellipticals, lenticulars, 29% lenticulars, and so on. Bulge to total light is one of the basic parameters that relates morphological types of galaxies. The bulge to total light ratio increases progressively from late type to early type galaxies. We investigate how the P by T varies with morphological types for cluster members, non-members and unknown redshifts. This parameter is distance independent, hence can be used to compare all three categories. Morphological types related to B by T, where ellipticals, lenticulars, your B by T lies between 0.8 to 1. For lenticulars, the bulge to total light lies between 0.5 to 0.8. And for spirals, B by T lies between 0.5 to 0.5. And as we see, the B by T lies between 0 and 0.5. Where early type galaxies, ellipticals, lenticulars with bars, and late type galaxies, spirals, barred spirals have separation at B by T 0.3. Goetze et al. In their paper 2004 have B by T greater than 0.6 for ellipticals and B by T 0.6 for ellipticals with disk. Bulge to total light ratio, including dwarfs, we classified them visually, and the visual types are given here in the first column. Ellipticals, lenticulars, and so on, ring and irregulars. And we have given the P by T ratio for members, non-members, unknown redshifts. What we notice from here, there are two galaxies with values of 0.13 and 0.18 which have been excluded as their edge-on. And in general, for SBOs and B by T less than 0.6, but one of the SBOs, barred spiral galaxies, B by T is equal to 0.907. These histograms give the morphological distribution with B by T values for cluster members, non-members, and unknown redshift galaxies. This is in agreement with others. In the figure, ellipticals, lenticulars are shown in red. Ellipticals and barred lenticulars are given in pink, and lenticulars SO are dark yellow. SBO light yellow, and spirals are shown in blue, barred spirals in green, rings in gray, and irregulars in black. So this shows you the how the B by T, according to B by T, the different morphological types. The limit of B by T varies for members, non-members, and unknown redshift galaxies. Coma members are in agreement with previous studies of Gutierrez and et al. And the late type galaxies have a separation at B by T equal to 0.3. Gutierrez et al. 2004 have given B by T ratio to be greater than 0.6 for ellipticals, and B by T greater than 0.6 for ellipticals and ambiguous with disks. In members, only one object that we classified as SBO has B by T 0.9. This classification is in agreement with Marinova et al. We also have compared B by T with non-members and unknown redshift galaxies, except for two objects in non-members, edge-on lenticulars, and three objects in unknown redshift galaxies. Our range agrees with Simeon and Devacular and Hassan 2007. These objects with unknown redshifts have an error in disk magnitude of 0.5. Non-members and unknown redshift galaxies have B by T values similar to the field galaxies. Galaxy morphology is related to the slope and scatter of color magnitude relation. A red sequence lies in the magnitude range of 13 to 22.5, and in our sample the majority of galaxies are ellipticals, lenticulars 9, ellipticals barred are 6, and SOs are 15, and SBOs are 11. And ring, there are 3 galaxies which belong to the red sequence, with the exception of 5 in which 3 are spirals and 2 are bispirals, which lie below the red sequence. Colors have been calculated from a source extractor for these 2 magnitudes, F814W and F475W magnitudes. Extinction corrections are from Ammer et al. We fit a solid line of the member galaxies and obtain the relationship which is given here. The figure gives you the color magnitude relationship for cluster members, non-members and unknown redshifts, galaxies and their morphological types. The solid line in this is the linear fit of the cluster members, and the band of galaxies with the fitted lines are called the red sequence. The spiral members are bluer due to the high star formation rates. Filled circles represent the members, cross marks represent the non-members, and open circles represent the unknown redshift galaxies. ESOs are red, ESBOs are pink, and SO dark yellow, SBO light yellow, and so on. So you see where they lie, and there is a clear segregation of where they populate the diagram. For the cluster members of our results are in agreement with Ammer et al. Members, ellipticals, lenticulars with barred lenticulars, SOs, SBOs and ring galaxies are in red sequence, and spirals and barred spirals are in blue region and have lesser color compared to the others. These are much brighter and have larger scatter from linear fit due to the star formation rates. Star formation can be introduced by cluster tidal effects of high-speed galaxy-galaxy encounters and also related to the environment of clusters. The color variations in galaxies can be explained by difference in the metallicity using stellar population models from Worthy. This diagram gives us the relation between the color F475W minus F814W by B by T for cluster members, non-members and unknown redshift galaxies with morphological types. And different colors indicate the ellipticals, lenticulars and so on. In general, the color relates to the age of the metallicity of galaxies, also describe the stellar populations. Both are distance independent and hence can be plotted for complete sample. We can clearly observe color of the galaxy increasing with B by T, and dwarf covers the range of B by T ratio, but colors are limited to F475W minus F814W less than 1.2, including spirals for members. The color of galaxies becomes red with increasing B by T ratio, except for dwarfs where the scatter is large. Ellipticals are redder than dwarfs. Barred spirals have similar colors as SBOs, and spirals have the color less than 1. Though we have only 5 spirals and barred spirals, we observe that barred spirals have a redder color in value compared to spirals. In general, we observe that spirals are in lower blue region, ellipticals are in upper red region, and lenticulars are in between, indicating the possible evolution in sequence. In the case of unknown redshift galaxies, a few objects are classified CMR diagram. The gal fit for these objects have larger errors which could explain the B by T, but the red color indicate the low star formation rates, probably due to quenching. The Cerseic index of galaxies is used to classify the galaxies as dwarfs n less than 2 and giants Cerseic index greater than 2. Barden et al. Van der Wel found through simulations that early type galaxies have n 2.5 and late types have less than 0.2. For a sample of 219 galaxies, we observed that Cerseic index of the galaxies in agreement with the previous studies, where Cerseic index of early type galaxies is greater than 0.25 and followed late type the Cerseic index is less than 2.5. We can observe this in Cerseic index distribution histogram. In the case of lenticulars, the faint ones have Cerseic index less than 2 and the brighter ones have Cerseic index greater than 2, which agrees with Wagner. In case of dwarf galaxies which have n less than 2, we have 9 member dwarfs with n greater than 2. These could possibly be dwarfs with nuclear star clusters and ultra compact galaxies. This diagram gives the morphology distribution with Cerseic index of galaxies for clusters, members, non-members and unknown redshift galaxies, and the color coding gives you the different types. In these figures, we show the relation between Cerseic index of galaxy and B by T for cluster members, non-members and unknown redshift galaxies with morphological types, and the relation between color and Cerseic index of galaxies for cluster members, non-members and unknown redshift galaxies with morphological types is given in the lower diagram. Except for 9 dwarfs, others are clearly in agreement with previous studies which were undertaken to classify early types and late type galaxies and dwarfs and giant galaxies. Their 9 objects might be ultra compact dwarf galaxies, nucleated dwarfs and non-nucleated dwarf galaxies. If you observe the color magnitude relation diagram, these 9 objects are exactly placed with objects such as UCDs and dwarf ellipticals and so on. Karmandi relation was found by Karmandi in his paper. He described it in his paper of 1977. In his thesis, it is the relation between the surface brightness of a galaxy and the effective radius. This fit shows the structural properties of elliptical galaxies, and later it separated, Karmandi separated the pseudo bulges of galaxies with this Karmandi relationship. This explains the secular evolution of disk galaxies, which are more similar to spiral galaxies. We have plotted the visual morphological types of galaxies. The middle line is the linear fit of ESO galaxies, and we have a slope of 0.03 plus or minus 0.398. The lower and upper lines are the 3 sigma elements. The galaxy slope is almost similar to Karmandi. So here is a diagram, the Karmandi relationship between the surface brightness of galaxy and the effective radius of galaxy. The SBOs are in light yellow, spirals in blue, barred spirals in green, and rings in gray. And the middle line represents the linear fit of ESOs, and upper lower lines are the 3 sigma limits. And we see that the ES ellipticals and lenticulars, they lie within the 3 sigma of this fit. To confirm our visual morphology, finally we use Karmandi relationship. This is generally given, this gives the information about elliptical galaxies and modified Karmandi relation with galaxy bulges. Gaditi in 2009 observed that the slope of the classical bulge is similar to elliptical galaxies. Finally, by involving the ellipticals and with boundaries, he classified the bulges. And we also observed that the slope of a sample of classical bulges and ellipticals have a similar slope with Karmandi ellipticals. By taking plus or minus 3 sigma boundaries of ellipticals, we observe that morphological types agree with Karmandi that all spirals, barred spirals, and dwarf galaxies are placed lower the 3 sigma line. Whichever the 9 objects didn't agree, Cerseic indices of the galaxies have agreement with Karmandi relation for galaxies. But lenticular galaxies placed above and below the line, we found that lenticular galaxies which are placed lower than 3 sigma are fainter than the others. To come to the conclusions, we have determined the morphology and structural properties of 219 galaxies from Hubble Space Telescope ACS central region of Coma Cluster brighter than zero point 0.9 in F81W magnitude. We confirm our morphology with B by T color magnitude relationship, Cerseic index, Karmandi relationship, and found correlations with structural properties. We found 132 cluster members, only 51 were non-dwarfs, one CD galaxy. Ellipticals, lenticulars are about 18%, ellipticals, SBOs are 12%, lenticulars are 29%, rings are 6%, SBOs are 22%, spirals are 6, and barred spirals are also 6% each. For 32 members, 28 were non-dwarfs, and again we see ellipticals SOs are 25%, barred spirals 11%, and lenticulars are 25%, and so on. Irregulars are 7%. For 55 unknown redshift galaxies, are 13% are ellipticals, lenticulars, barred lenticulars are 13%, and SOs are 29%, and spirals are 27%. Irregulars are merely 9%. We present bulk disk decomposition of sample using GALFIT and obtain parameters for a sample. Using visual inspection of residuals, we do a morphological classification of galaxies. We study the relation of morphological types with bulge to total light ratio, color magnitude relations, Cerseic index, Karmandi relation, and cross correlation between these parameters for bulge and galaxies. This work helps us understand the important relations between various parameters like bulge to total light ratio, color, and the Cerseic index, as well as insights into the merger history of these galaxies in terms of their position in the Karmandi diagram and their Cerseic indices. Using statistical methods, we find that there are significantly more ellipticals SOs and the lenticular galaxies in the member populations compared to the non-members. Thank you.